Hello and welcome back to another lecture on advanced plasticity of solid continua, an NPTEL course. As you would recall, we have been discussing about thermo-viscoplasticity. So in the last lecture we started with the convex analytic approach as always, so that we can use a variational route. So we started with the phi star, which is basically the dual to the dissipation, and then defined through the Legend differential transform the dissipation potential. And in the process we also started discussing a few such yield functions that can be used in Perzina-type thermo-viscoplasticity models, because Perzina-type models has a rate independent part in it, and that in turn requires the definition of an yield function and hence an yield set. Alright. So in that process we discussed two such functions, yield functions. One was the temperature dependent von Mises type isotropic hardening, this function, right. Another was Johnson-Cook type yield function. Now let us talk of another one, another two at least. Okay, so this is a thermally activated Arrhenius-type yield function. Now you see that this Q is common to all the cases. We have an initial yield like thing sigma 0, yield stress like thing. This is the hardening part, isotropic hardening part, and this is the thermal effect which is captured through this activation Q. Q is the activation energy, R is basically a constant, a gas constant or whatever, So theta is the absolute temperature, right. So this is very useful for capturing the thermally activated plastic flow, okay, where you think that thermal activation is very important in defining the plastic flow. It is very useful. So it also fits in very well with the Perzina type laws, okay. So therefore this is one more, and then we can also talk of a saturation type hardening, all right, such that the hardening does not happen all the time, right. So define a saturation level sigma s, that also can be a function of theta, because saturation level stress can be reached for different temperatures, it will be different, right. So sigma is 0 is the initial thing, right. It can also be a function of theta, okay, and there is a thermal part multiplying this factor, this part, okay, sigma s minus sigma 0, okay. So as you see that both initial and saturation stresses, this is the saturation stress, okay, they may depend on temperature. This is very useful for cyclic plasticity and for large strain accumulation problems, because if the plasticity is cyclic, you should realize that the problems could involve large accumulated strain over a large number of cycles, right. So this is very useful for such problems. So understanding which one to use for which problem is not just a matter of learning something from the course, but also it is a matter of, if you work hands on with things later on in your industrial experience. So those of you who are actually working in the industry, they will be knowing already that which model to use for which cases, okay. So right, now we come, so having discussed a few such yield functions, we are now ready to talk about the variational formulation of our thermo-viscoplasticity problem, okay. So let us do that. As always, we have always this one to fall back on. This is the rate functional, rate potential density, rate functional, whatever you call, okay, rate potential or rate functional, that is the typical name. So that replaces the strain energy of elasticity in this particular case. So you take variation of strain energy in elasticity, you take variation of pi here, right. Sometimes okay, I mean a local variation, you know, if you take a local variation that is pointwise at the Gauss points, if you take the variation of pi, the rate potential, then you will be getting what is called, you know, if you take the variation with respect to the internal variables, dot of that means the rate of the internal variables, then you will be getting what is called this, you know, this flow rule, right. If you integrate this over entire omega, entire body, and then over time if you discretize this and then take the variation, then you will be getting the governing equations, like the governing equation for deformation. If you take the variation with respect to deformation, then governing equations for, you know, for determining this, you know, this alpha dot and u, that is the displacement, together, all right. So let us, so these are, taking the variation of pi, you can get the Euler-Lagrange equations. So for example, you know, take variations, so any such functional, if you take a variation and get hold of some governing equations, you know, they are the equations of motion, which are called the Euler-Lagrange equations, right, you may be knowing about it. So now these Euler-Lagrange equations are the ones for which you know, the FEM tries to solve these by using the weak form, right. So for example, this, you know, the linear momentum balance, the local form of it is an Euler-Lagrange equation from the variation of the strain energy, right. So similarly, we are going to define the appropriate Euler-Lagrange equations in these plasticity problems. So now let us first split the free energy part, which is basically psi, the Helmholtz free energy, in three parts. One is the elastic part, okay, the second is the plastic part, and the third is the purely thermal part. Now of course, I mean the elastic part will be purely dependent on the elastic strain, which is defined in terms of epsilon, the total strain, minus the plastic part of the strain minus the strain due to the thermal part, okay. So that is my epsilon E, right, that is the elastic strain, which is also written here. So psi E, the elastic part of the free energy, psi, is only a function of the elastic strain. Now let us do the Euler-Lagrange equations, all right. Observe that the psi dot, by just chain rule of differentiation, I can write it as del psi by del psi. This is the standard thing that we have been doing for quite a long time, observing that psi is a function of epsilon E, alpha and theta, all right. Now you know, you take the dot of the, take the rate instead of epsilon E, you take the rate of it, which is related to the rate of the total strain epsilon and the plastic part and the thermal part, this way, it's trivial. Now introduce the standard thermodynamic quantities, okay. These standard thermodynamic quantities are also based on basically the Coleman-Knoll procedure, which we have already discussed in great detail, and you will be getting basically these closure relationship. For example, sigma is del psi E by del epsilon E. This x, the thermodynamic force conjugate to alpha dot, will be minus del psi by del alpha, and eta, the entropy, is minus del psi by del theta, okay. Therefore, you know, using this I can write psi dot in terms of these closure conditions. That means sigma inner product with epsilon dot minus epsilon p dot minus epsilon theta dot, minus x inner product with alpha dot, and eta minus eta theta dot, right. Correct. So let us now, in our since our purpose is to derive the Euler-Lagrange equations, we need to take the variation of the entire rate functional or the rate potential. So write the rate potential pi, this is the first part, okay. This is the part corresponding to psi dot, which we just saw in the last slide. This is the rate independent part, phi r I, phi is the dissipation potential. This is the rate dependent part, eta is the viscosity. Okay, if eta equals 0, then of course this is gone. This is the rate dependent part of the potential function. Sorry, the dissipation potential function, and this is the thermal part. Okay, so we have added everything, all right, psi dot plus phi. Okay, so for the variational problem, so now we have to take the variation of pi and set them to 0. That is the objective, and in the process we get the Euler-Lagrange equations, right. So we have to take the variations of pi with respect to which quantities? All the rates, I mean except for theta dot. We have already got the relationship eta equal to minus del psi by del theta. There is a single hanging term here, so so we have to actually take the variation with respect to epsilon p dot, alpha dot. These are the internal variables, rates of internal variables arising in plasticity, and the thermal variable heat flux q. Okay. Now let us do them one by one. Okay, and we have been doing this also for other problems. In the last in some lectures prior to this, we actually took the variations of pi exactly in this way, but we did not include temperature. Heat transfer was not included in the process. So this is a repetition for you, so I may not actually I may go a little faster. If you have any difficulty at any stage, what I suggest is that you take that wherever you are finding it difficult, that some formula, if you do not understand, even after my explanation, what you do, you actually take a pen and paper and try to derive it yourself. You will see things will become much clearer. My suggestion to you is to use pen and paper. Okay, not just listen to it, but use pen and paper to derive everything. So let us first take the variation with respect to epsilon p dot, variation of pi, the rate function. So okay, now look for those terms in pi which depend on epsilon p dot. Only those variations are meaningful, right? So the terms which depend on epsilon p dot are these. These are listed here. Okay. Now the C is defined in this way. That's why. Okay. So now let us use the standard, the variation. So basically we need the variation of the first term, the second term is lambda, we take the variation of that also. Okay. So the subdifferential, I mean we are talking of subdifferential whenever we basically have functions which are everywhere smooth. Subdifferentials are nothing but gradients. You must remember all the time, so that the word subdifferential should not make you uncomfortable. Okay. So the subdifferential of lambda, right, that we need to find, and then anyway let us write this del pi. Del pi means here, del pi, by that I mean maybe I should have written that way, epsilon p dot pi. That means you are varying epsilon p dot, taking the variation with respect to epsilon p dot. First term is simple from here. Okay. The second term, second term is delta epsilon p lambda, epsilon p dot lambda, that is taken as a factor because lambda appears here too, right. So together do it, because lambda is a function of epsilon p dot, please remember that. Go back to the last lecture and look up the definition of lambda as the dual norm, okay. So which depends on epsilon p dot and alpha dot also. So then you take this as the factor, okay, this comes out as the factor, and then there is a final multiplication with an appropriate inner product dot with delta epsilon p dot. This is my total variation, right. Now I need stationarity, that means stationarity means delta pi has to be equated to 0. This is true for all delta epsilon p dot all admissible variations. So, delta epsilon p dot being non-zero, it cancels out and we basically simply have this relationship again, because we are actually writing as if things are not everywhere smooth. That is why this 0 belongs to that sort of symbol is there. Basically it means 0 equals to provided things are smooth enough, okay, because stationarity gives you delta pi equal to 0 and that 0 equals this, okay. This is how it is. If not, if there is a loss of smoothness, of course it becomes you cannot write 0 equal to the right hand side, you have to say 0 belongs to this, okay. So, anyway, now let us, so from here we see that we basically got a relationship sigma equals to, let us say that things are smooth. So, sigma equals to this, right. Okay, so now we will take the variation with respect to alpha dot, okay, that also let us do. So, delta pi with respect to alpha dot is also 0, and if you do the details then you get this, okay. Please write them yourselves on a piece of paper and ensure that every formula you understand thoroughly, so that you can proceed forward with a full understanding of the subject. And we have the same condition now. Now instead of sigma we have the other thermodynamic force x coming in here instead of sigma, right. That is conjugate to alpha dot, that is what is expected anyway, right. Since earlier we took the variation with respect to epsilon p dot and sigma is conjugate to, thermodynamically conjugate to epsilon p dot, that is why sigma came there, okay. So, define the full set of generalized forces, combine sigma and x together in the variable this capital sigma, okay, and combine epsilon p dot and alpha dot together in this variable capital Z dot, capital Z dot, okay. So, now you have basically a combined equation by setting delta pi equal to 0 with respect to variations with respect to both alpha dot and epsilon p dot, combine them. So, sigma, capital sigma equals this, okay. Instead of belonging to, you read it as equal to, provided things are smooth, alright. So, this is my Euler-Lagrange equation basically, that is what we get, but then we can actually simplify it, because we have still to do this, we can simplify these quantities, okay. We can so first of all you basically recall that in terms of this combined variables z dot, lambda is the dual norm of z dot, right. And now we can use the fact that whenever you basically are taking the derivative of lambda, this is a derivative with respect to rate like quantities, okay. So, you get generalized force like quantities, and these forces have to be normal in the same way that we have been discussing normality in plasticity, okay. So, therefore, you can think of delta lambda, which is the subdifferential of lambda or the gradient of lambda, to be very simple, to speak simply, with respect to the rate variables. They give you the force like variables, and that has to be equal to gamma by normality. It has to be basically along del f by del these derivatives, and times gamma, okay. Gamma is the factor, this factor comes out to be equal to this, alright. So, you just rearrange this, basically so the best thing is to actually for you to do this with a pen and paper. So, differentiate lambda first, that is norm of z dot, you get z dot on top divided by norm of z dot, like that, right. Recall that norm of z dot is lambda itself, right. Rearrange properly and make sure that you come to this expression, right. This is nothing but this equation, okay. This is nothing but this with appropriate modifications, right. So, what we basically get in the process by taking the variation of pi, the rate functional with respect to these rate type variables epsilon, p dot and alpha dot, is the flow rule, and that has to be the Parzinov flow rule, right, correct. So, this part is quite understandable. I mean, always the local variation, that is every point wise we have done it, right. So, we have not integrated pi over the entire domain of the body and done it point wise. So, we basically always in doing so we recover the Parzinov flow rule in the rate dependent, but without any thermal transport, heat transfer. In those cases we have already seen this again and again, that there are two parts in the optimization which finally leads to the solution to the plasticity problem. One is a local thing, local update, which actually recovers the flow rule, and the other is the global or structural update, which is done after integrating pi, the rate functional, over the entire body, right. Now let us also, for that matter, take the variation of this pi with respect to the heat flux Q. So, this is also pretty simple. You expect, if you take the variation of pi with respect to Q, then you expect to recover Fourier's law, Fourier's heat conduction law, right. That is what precisely what is happening. Q is minus cap k theta times G, where G is grad theta by theta, okay. So, basically G is basically defined as minus grad theta by theta. You recall that we have already defined it in the lecture before the previous one, okay. So, anyway, so this is essentially the Fourier's law, okay. So, that is what is expected, right. So, basically what we have done is that this is an important point, that basically in thermo-viscoplasticity we have constructed the rate functional, we have taken the variation of the rate, we have appropriately put in the simplifying things based on the Coleman-Knoll closure, because we have used things like sigma equal to del psi by del epsilon E and things like that, eta equal to minus del psi by del theta to write psi dot, the time derivative of the free energy, properly. And through this variation of pi, that is through by applying the local variational principle here, we have got the Parzinov-type flow rule, okay. Then we have got also the fact, because we have been using the dissipation potential in such a manner that the rate independent and the rate dependent terms are separated. As soon as the eta, that is the viscosity parameter, actually I should call it mu, right, mu I think, or whatever it was there. Let me check what was it, in the viscosity, what was it, eta or mu, because eta we are using, this is basically, ideally you should replace it by mu, because eta we are using for entropy. This is one of the problems, okay. So, let us call it mu, mu is the viscosity, okay. So, as the viscosity tends to 0, right, the relation reduces to the rate independent case, and we have also got the Fourier like law in the process of taking the variation of pi, the rate functional, with respect to Q. Now, I should actually I have been telling you about the thermodynamic consistency, right. We have been saying that whenever you basically talk about objective functional which are convex, phi is convex, the dissipation potential is convex, and whenever you talk of strictly convex dissipation potential, or at least convex dissipation potential, your dissipation has to be positive. That means thermodynamic consistency has to be maintained. I think this particular point earlier I said this several times, but I will try to explain this briefly to you. you remember the definition of the convex function, right? So so let us say that phi is a function of j, right, phi j. Now take two such rates. Phi is always a function of rates, right, some rates. Now take two such rates, one is j star and the other is j. They are not the same. J star is different from j, right. So since phi is convex, we can write phi of j star will be greater than equal to phi of j, correct, plus del phi means grad phi, basically grad phi or del j phi, right, at j times j star minus j, correct. J is a rate, remember that, correct, and del phi j is the thermodynamic force corresponding to this rate j. That is true. So therefore we can write this by a force, you can call it x, let us say x, okay. So what now, let us take j star equal to 0. For these convex functionals, always phi 0 is always 0, okay, that is a requirement. So our requirement is that phi at j equal to 0 is 0. So the minimum is attained at 0, okay, the minimum of the function phi is attained at 0. Away from j equal to 0, the function is strictly positive because the minimum is there at j equal to 0, right. So for j not equal to 0, the function is strictly positive. Now in this equality, you take j star equal to 0, then what happens? You see that take j star equal to 0, then what we get, 0 greater than equal to phi j. J star equal to 0 means phi 0 is 0, right. So phi j, right, plus this thermodynamic force x, 0 minus j, right, 0 minus j is minus j. So basically what we have is that x, if you take this x dot minus j on the left hand side, then you get x dot j is greater than equal to phi of j. You understand? So basically, but since j is away from 0 because j star was 0, right, and so j is different from j star, so phi j being strictly convex is definitely greater than 0. So you see that x dot j is nothing but the thermodynamic force acting on the rate j and producing dissipation. So you see, for a strictly convex phi, we have got the dissipation definitely greater than 0. If it is not strictly convex, then of course it is greater than equal to 0, okay. So this is an advantage of using convex functions. So this is what actually we wrote here, thermodynamic consistency is maintained. So we will be always be having this relationship, that is x. So here x contains both sigma and this x, right. So basically all the forces, and they multiplying they are multiplied by the corresponding rates, and they give the dissipation greater than equal to 0. For strict convexity, it is strictly greater than 0. So that is a very useful thing. You remember that strict convexity is phi is assured for the Perzina-type model, right. So now this is all about this lecture, okay. So this lecture we have more or less done. Another question, so we have been discussing this for quite some time, but we have not explained why. It is like this. Why is this rate functional psi dot plus phi a valid thing to be minimized, for which we will be getting by doing which we will be getting the solution? That question can arise within you. So we will try to explain this. This is asking a question, a similar question in the context of elasticity will be that why is it that minimizing the strain energy gives you the solution? People typically assume it, right, but in plasticity this has other meaning, this has a deeper meaning, in the sense that things are basically quite random, and from experiment to experiment this randomness can actually come out, even though there will be a general trend So, a determinism is still valid, but a randomness can come in. So, the question that we will be answering is, why is a valid thing to minimize to get the solution for the plasticity problem? That is one thing we will be discussing. And the second thing we will be discussing is the time discretized solution of this entire thermo-viscoelastic problem via the finite element analysis, which we can actually implement in a computer, right. So, these are the things which we will be discussing in the next class. I hope you are enjoying whatever is being done in this slightly advanced course on plasticity, and I hope you are enriching yourself with some knowledge which I am trying to provide you with. So, we will again meet in the next class. Thank you very much for your attention.